La verdad que para mí y para los que trabajamos en Campus Party desde hace ya bastantes meses y bastante tiempo, es un enorme honor poder ver esta realidad, poder ver esta super experiencia tecnológica como la más grande que hoy en día hay en la Argentina, y con los disertantes internacionales que tenemos todos acá y con la presencia que vamos a tener a continuación. Así que sin mucha más introducción, y estamos ya en horario para poder presentarlo, para los que ven por live streaming también. El próximo orador internacional es John Maddog Hall. Él es promotor del software libre. Un aplauso enorme, por favor. Él es promotor del software libre, como los más importantes, uno de los cofundadores de Linux y actual director general de Linux International. Así que, sin mucho más introducción, un aplauso enorme para John Maddog Hall.
Thank you.
John.
Thank you. That is probably the last time you will see me run during Campus Party. Today I'm going to do something different than I normally do. Normally I talk about business and free software and how to make money and save money with free software. And you're welcome to come and talk with me anytime you see me at Campus Party to talk about those things. But today I'm going to give a more technical talk for people because we're not programming in 1969 anymore, nor are we programming in 1984 when the GNU project was started. Computing has changed, and I will show you how it's changed and how it might change in the future. First of all, I would, however, like to give a plug for my friends in the Sys Army people, whose little sign is standing up back there. Come and talk with them. They're great people. They have a group of systems administrators, and they're local here, and they just want to help you find out more about systems administration and computers in general. Last night we went out. We had a great time, and they're actually friendly. They're not the bastard operators from hell that you always hear about, so go and see them. And finally, if you want to get a little bottle of deodorant that they have, I've been told in Spanish that the word sudo means to perspire. So sudo hyphen is don't perspire. Instead, learn good systems administration and you will be fine. Now, a lot of people look at me and they see an old man with light beard and hair who perhaps gives out Christmas presents in the form of free software. Ho, ho, ho. But actually, at one time, I was as young as you are. In fact, I was even younger, they tell me. And I studied back in 1969 electrical engineering, because back in those days, there was no such thing as computer science. There was only computer black magic. There was no such thing as a professional programmer. In fact, I had a professor of mine tell me to my face, John, you will never be able to earn a living as a professional programmer. And I'm still waiting to find out if he was right. But I also studied half business. So while I may not be able to design a CPU and get it working properly, or maybe I have trouble in running a company, I can tell when engineers are lying to me. I can tell when business people are lying to me. And of course, politicians lie all the time. But we also studied a little bit of this magical thing called computer software. Uh-oh. That means I'm not getting power to my system, and my battery is running down. Let me see. Why am I not getting power? Pardon me for a moment, as I'm trying to figure out why I'm not getting power to my system. I don't know yet. Oh, now it's okay. Sorry about that. Now we go through this. Sys Army, friendly. Oh, here we are. But I did do a lot of programming. I programmed on mainframe computers for 5 years, and then I met Unix, and I loved Unix. And then in 1994, I met Linus Torvalds, and I helped him port Linux from a 32-bit processor to a 64-bit processor, and helped him to make Linux portable. I've worked for lots of companies, both large and small, but mostly I've been a programmer and a systems and a university educator, and that's what this talk is going to be about. In May of 1994, I saw Linus and Linux for the first time. I helped to assemble an engineering team to help make Linux more portable. And then in 1995, I started forming organizations like the Linux Mark Institute to defend the Linux trademark, Linux Professional Institute, which certifies systems administrators, and the Linux Standard Base Project. And since 1995, I've been traveling the world trying to promote Linux. Now, the main subject of this talk is the question of who needs performance. I mean, aren't CPUs fast enough? Why do we need CPUs any faster than the ones we have today? Well, I actually had somebody ask me this question one time, and I said, you know, until the CPU is so fast that I can talk to my computer and it can understand me at least as well as you can understand me, then it's not fast enough. A lot of other people say, Java is the only language you need. I don't believe that. I believe that Java is a good language for what it was intended on the client side of the situation, where you don't know what operating system you have, you don't know what architecture you have. So Java is a good language for that. But on the server side, you know exactly what architecture you have, you know exactly what the operating system is, and you need a language which is efficient and small, and one that gives you control. So I will believe that Java is the be-all, end-all language when Larry Ellison rewrites the entire Oracle database in Java. And that will happen when there are snowballs in hell. Other people say to me, nobody codes in assembly language anymore. I spent the first 7 years of my professional life programming in IBM assembler language because our computer systems back then, our mainframe computers, had 1/4 of a megabyte of memory. And they cost $2.5 million. And that's when $1 million was a lot of money. But I'm happy that people don't code in assembly language anymore, because assembly language coding is hard, and it's unportable, and it really helps you create bugs. But on the other hand, you need assembly language, and I'll show you why later. And this is another one I love. Virtual machines make the knowledge of an architecture obsolete because they remove the actual architecture of the machine from you. And I think that's a very dangerous thought, and I'll tell you why later. A lot of people say to me, do you like games? Do you like computer games? I hate computer games, I really do. I probably played a computer game 5 times in my whole life because I think all of programming is a game. Writing a program and getting it to work is instant gratification. It's better than drugs because drugs take time to work. And then drugs take time to get over. But when you solve that problem and it works, nobody has to pat you on the back and tell you that was a good job because you know it. I love programming. But I like real programming. And real programming for me is either tiny little things, and getting them to work well, or really big things. Petabytes of data, 10,000 cores or nothing. If you don't have a problem like that, please don't come to me because I'll charge you a lot of money for doing ridiculous work. Another thing that interests me is real-time programming. And I'm talking about real time. Like when your nuclear power plant is melting and you have to lower the rods to stop it. You don't want a Chernobyl. That's real time. And one time, I was talking with Linus Torvalds in the early days of Linux. And I said, Linus, it would be good if you made the real-time work inside the kernel work better. He said, what's wrong with it? If I'm playing the game of Quake, and the monster has a gun in its hand, and it goes to shoot me, and I hit the button, and I kill the monster, that's real time. I said, Linus, put a real gun in the monster's hand, and see if you feel the same way. And there was silence on the other end of the phone for about 10 seconds, and he goes, I see what you mean. And the next release of Linux had much better soft real-time support. There's another way of looking at this, and it's due to an IBM study that was done probably 30 years ago, where IBM studied the human brain and said, if the human brain asks a question, a relatively simple question that it expects that the answer is going to be relatively simple to give, the brain expects that to come back in actually a third of a second. 3 seconds is the longest that the brain is going to wait for that answer. Now, why is this? And you've all experienced this, I'm sure. You're working away, you hit the enter button, and all of it, and you're looking for the answer, you're thinking, you're concentrating on it, and then all of a sudden, oh my God, look at that person. They are so beautiful. What was I thinking about? And it takes you time to come back and concentrate on that problem again. But if you hit that return button and the computer comes right back, you don't even look up. You're still asking the next question. We need to have that type of response, and we don't have it. And therefore, computers are not fast enough. Here's another way of looking at performance: cell phone applications. Now, you don't want your cell phone to talk faster to you. You can't understand what it says. You want your cell phone to deliver the audio at a rate that you can understand it, at a rate that you expect it. But on the other hand, you want your battery to last a decent amount of time. So whatever your cell phone is going to do, you want it to compute it right away and then present the data to you in the form that you want to see it. You want your battery to last longer. You want your program to be more efficient. That is also performance. And it's not just about cell phones. If you're Google and you want to have 10,000 servers in your server farm, if your programs are 10% more efficient, it means you only have to buy 9,000 servers instead of 10,000 servers. And the electricity that goes into running them is only 900 megawatts instead of a gigawatt. And the air conditioning to cool them may only be 900 megawatts instead of a gigawatt. And that ends up being real money. And also saves the environment. And finally, we're starting to be able to get some different types of processors that we have known how to do for a very long time, but they were just too expensive. Now, some of you may remember when Intel came out with the first 386 processor, it did not do floating point arithmetic. No computers, well, very few computers back in those days actually did floating point arithmetic. Most of the operating system was written to do integer arithmetic, because when you started to do a floating point number, it had to be emulated in the software by doing integer work. And finally, you would put in something known as a floating point accelerator. And when that piece of hardware was in your system, all of a sudden, all of your floating point calculations would speed up dramatically. But for little PCs, the people didn't want to spend the money, and so they tried to avoid floating point arithmetic every time they could. But Intel came along and created a floating point accelerator chip. So you would buy your 386 processor, and then you would put this floating point accelerator chip onto your board for extra money, and now you could do fast floating point arithmetic. After a while, Intel realized almost everybody is buying that chip. So what we'll do is we'll take those floating point instructions and put them onto the main CPU. And now most CPUs you have that floating point accelerator, those floating point registers built into them. It's the same type of thing that's happening with some new things coming out, like digital signal processing chips. As more and more people use them, as the price of those come down, you'll find more and more systems put those into the computer system you buy, almost for free. When I started off in computer science, I would actually build floating point field programmable gate arrays. But they were huge, and they would fill half of this floor, and it would require so much electrical power to run them that very few people could afford them. But today, you can get them for only a few dollars, and we'll see how those are going to be changing things later on. So this is the second computer I ever programmed. It's called a PDP-8. It was made by Digital Equipment Corporation, and it had 4,000 12-bit words. That was it. Everything had to fit into that. Your program, your data, everything. And it didn't have any disk drives. There was no such thing as virtual memory. You actually you didn't have an operating system. Your program was it. Your program had to talk to each device, and you had to do the programming. And a lot of times you would sit there and worry about whether you pulled the device and just basically wasted the CPU cycles, or whether you went through all the trouble of setting up an interrupt, because that might take 15 or 20 assembly language instructions. And I learned assembly language from reading a book. I'd never programmed in assembly language before, but I found a book for the PDP-8 and I taught myself. It was a very simple assembly language, but it taught me how the computer actually worked. And I really believe that to write really great code, you have to understand how machine language works. You have to understand what the architecture is. And that includes learning machine or assembly language of at least one computer. Now, how did I use this knowledge once I had it? In the early days of my work with a very large insurance company, we had a COBOL compiler for the COBOL language. And one day I had one of the programmers who wrote in COBOL come to me and say, I can't find the problem with my program. Now, I didn't write in COBOL, but I did know the language. And I looked at the person's program, and I said, I don't see what's wrong either. I think the compiler made a mistake. And the programmer goes, "What? The compiler made a mistake?" I said, "Yes. The compiler is a program, just like the one that you write. And just like your program, the compiler writer came downstairs on a Monday morning, still hungover from the night before, scratching themselves, sitting down, realize that they have to submit their code into the pool before they've had their first cup of coffee, and they put it in, and they didn't test it, just like you don't." And so we told the compiler to generate the assembly language so we could look to see what was really happening. And yes, we could see that the compiler was making a mistake. If I didn't have the knowledge of that assembly language, we could have looked at the COBOL source code for the rest of our lives and not seen the problem. In the IBM system, the IBM 360 system, there is this instruction called read the clock. Sounds rather innocent, doesn't it? Read the clock. Anybody, most computers read the clock, could do it really quickly. But it turned out that this one instruction was taking up 99% of the time that the program ran. And only if you knew assembly language would you figure out that every time that instruction was executed, everything in the entire IBM system came to a halt, because read the clock was used to synchronize all of the actions of the machine. Not only that machine, but every other machine that was even remotely attached to it, because read the clock was used for synchronization of the entire CPU. Again, if you didn't know assembly language, you would not figure it out. EBCDIC is a code a lot like ASCII. And EBCDIC was unique to the IBM systems. There were 4 instructions that were the slowest instructions in the whole machine. One of them was to take an EBCDIC number that you could read and change it into something called packed decimal. Packed decimal, you could actually do arithmetic on it, but it was very slow. Then there was another instruction that would take packed decimal and change it to binary. And binary, of course, was used at things like an index into an array or something like that. Well, if you used in COBOL, if you said a picture 9 field, that forced the compiler to hold the number, to hold the index to your array in EBCDIC. So every time you accessed your array, the computer would have to do EBCDIC to binary to packed decimal to binary. You would increment it by 1, access your data, then you have to store it back, binary to packed decimal to EBCDIC. Billions of times every minute. If you had just said, store it as a picture 9 comp field, that tells the compiler, always hold it as binary, never convert it. And now your whole program goes about 1,000 times faster. You know that because you know assembly language and you know what the compiler is going to generate. We worked on the digital Unix operating system, which back in those days required 64 megabytes of memory to boot and run efficiently. Folks, that's 64 megabytes of memory. This is a server system that is running in something a lot smaller than most of your cell phones. Okay. And our product manager said, no, there's too much memory. It has to boot and run efficiently in 32 megabytes of memory. And all the engineers groaned and moaned and cursed and stuff like that. But after years' time, they had taken all of the fat out, compressed the system, and got it to run in 32 megabytes of memory. And we thought the system would run a lot slower. but actually it ran 7% faster. And the reason for that was that the alpha processor that we ran the system on had a huge amount of cache memory between the CPU and main memory. By shrinking the operating system, we kept more of the operating system in the cache, and so fewer times it had to go out to main memory. And so it ran faster. I worked on a system on a PDP 1170 mini computer one time that it took 10½ hours to sort 1,206 32-byte records. I told the person that wrote the program I could have done it faster by punching it onto cards, throwing them in the air, and picking them up off the ground. I rewrote the program to keep most of the data in memory at one time. And the program time went from 10½ hours to 3 minutes. And again, it's because I knew what the architecture of the machine could do. Now, today, a lot of college students go to university and they learn Microsoft Office and Oracle. You say, what are you studying in university? Oh, we learned how to use Microsoft Office and Oracle today. And I cringe. Have you learned any other operating system? Any other Office system? No, just Microsoft Office. So you really don't know how to choose which Office system you should be using to do your work. They're learning Java and something called IT, whatever that is, instead of assembly language and operating systems. And they're always using virtual machines instead of using the real iron and seeing how it really works. High school students are even worse because they go out and they buy this computer, maybe a laptop, and on that laptop there's a magic phrase, you open this up and you invalidate your warranty. And so they're afraid to open it up because they spend a lot of money on the laptop, and if it breaks, they want to be able to take it back and get it fixed. And then they buy some games and put it on there, and they run the games, and then maybe they write some HTML, and they say, I can program. And so high school students tend to think of their computer like this. They tend to think that the computer is my friend. We all know that's not true. The computer knows you're out there and it hates you. Oh yes. In fact, this is how computers really look. And it's pretty terrifying, I think. And the problem that this created, that was recognized by the professors at the University of Cambridge, was that students coming into the university knew less about computers today than they knew 20 years ago. Because 20 years ago, you would have something like the Amiga or the VIC-20, and you would have to have a modem, and you'd have to dial up some bulletin board, and you'd have to pull down this program written in some language and get it to work on your system. And so you understood something called a syntax error. And once you finally got it to compile, then you understood a runtime error, register overflow, all these weird things that you never find out about if all you're doing is using Microsoft Office and a few games. And so the professors at the University of Cambridge created a Raspberry Pi to try and make it so that their students would actually see what a computer looked like in reality and work with it on that level. And the Raspberry Pi was a nice little computer. They had a goal of having it less than $35 US. But because of that, they made a lot of compromises. It ran relatively slow, 700 megahertz, with an ARM processor. and a half a gigabyte of memory. But the worst part about it was that everything went through the USB 2.0 bus, which is, as you know, an incredibly slow bus. 418 megabits a second. Slow. But it was very successful. They thought they'd only need 1,000 of them at first, and then say, well, maybe 10,000. And before they took their first order, they knew they needed 100,000. And in the first year, they made about 1.5 million of them. And today, they've shipped 12 million Raspberry Pis. But other people kind of woke up to this and said, oh, we can make something a little bit better. Oh, I should tell you something else about the Raspberry Pi. I really like it. I like the Raspberry Pi. I think it is a wonderful system for elementary school children. Just like I don't like games, I don't like really simple computers. The Banana Pi was a little bit better. It has 2 cores, so now you could do a little bit of interesting programming with race conditions and things like that. You have 1 gigabyte of RAM. You have a 3D GPU. But most importantly, you had a SATA controller on it, so you could hook a disk drive on. Then the Raspberry Pi people responded with the Raspberry Pi Model 2, a little bit more RAM. They had a quad-core processor, so a little bit more interesting, but they still had that USB 2.0 controller. There's just so many other computers out there which are more interesting than that for various type of reasons. I could go into all of these and be happy to do it, but I'm running out of time, so I'll have to move on. This is another interesting computer. This is an 8-core, 64-bit system, which costs about $100 US. And it has on it, up at the top of it, a high-speed bus, which you can plug a daughter card on with an Arduino, so you can do really good Internet of Things problems at the same time as you're gathering the data to process it. More interesting, right? Then there's the Maker Guitar. This is 4-core, 32-bit, and 2 gigabytes of RAM. But it has USB 3 on it. Thank God. And USB 3, you can take a very inexpensive cable and hook it up to a SATA disk, and now you can get decent throughput. Not only that, but there's 3 motherboards that go along with this, and you can actually create a 16-core, 8-gigabyte supercomputer out of putting 4 of these cards into one motherboard. The BBC, the British Broadcasting Company, has created a little system called the Microbit, which they're giving away to 7th graders and teaching them how to program. And every single 7th grader in Great Britain got one of these for free. And they're actually working it into programs like Doctor Who to encourage the children to do better programming. Now, why am I showing you all this? Because this gives you a chance to do something like this. I built this supercomputer, it's a Beowulf supercomputer, out of 6 Banana Pis. And it has 8 ports, switch on the bottom, at the very bottom of it, with 2 1-terabyte drives that are failover with RAID. And I can program this any number of ways. Oh, by the way, it folds up into that briefcase, so I can take it around and show it to people. I can use this to show people how to program high-performance computers or how to do high-availability programming. I can put all of the same operating system on all of it and do homogeneous programming, or put different operating systems on and do heterogeneous programming. Now, I spent $500 US in building this, and I ended up with a system that had 12 cores, but with this little system, I'll be able to increase it to 96 cores, which would be fairly powerful, and it all works off of solar panels. So it doesn't need really that much electricity. The problem with GNU Linux is that it's patterned after an operating system that was designed in 1969. That's not a bad design, it's very flexible. But a lot of the code was written in 1984 and in the early years of GNU Linux. And since that time, memories have gotten larger and cheaper. CPUs have gotten faster with more cores. Algorithms of how you do things change. If you have a small memory space, like a 16-bit memory space or a 32-bit memory space, use one type of algorithm. But if you have a 64-bit space, you might use a different algorithm, which could give you either greater efficiency or faster performance. We didn't even, when I started in programming, cash was money that jingled in your pocket. And today, cash can mean that your program can go 100 times faster if you utilize it well. Pipelining was something you did when you're putting in plumbing in your house. But pipelining today means, again, an order of magnitude faster programming. The GNU compilers back in 1984 were 30% less efficient in producing code than commercial compilers. But today, they're within 1 or 2% of the same performance as a commercial compiler, so why not use them? And a lot of people think that because of this, the need to code in assembly language has decreased. And they're right. We shouldn't really be coding in assembly language anymore, but we still need to understand it. We need to understand it because of the 500 fastest computers in the world today, 486 of them run Linux. And basically the same Linux kernel that I have here on this notebook. It's just you use a couple of extra libraries called message passing interface or parallel virtual machine. GPUs are not just for graphics anymore, they're used in computation, Bitcoin mining and things like that. You need to understand how the GPU works so that you can write those type of programs. And then we get to the field programmable gate array, which now is this tiny little thing in the middle of this card that you can buy this for $21, and you can write a program in the field programmable gate array which will be 100 times faster than one that you use in a traditional CPU. But you have to know how to program it. There are more and more CPUs that actually have field programmable gate arrays built into them. And several times on this trip, people have asked me about quantum computing, and I quite frankly say, I don't want to hear about it. I'm 4 years away from retirement, and if I can avoid quantum computing altogether, I will be happy. But most of you will not be able to avoid it. And so you'll have to learn about it, you'll have to learn how to program it, and you'll have to learn how to program it efficiently. So here's what I consider to be a university student's computer. It's got 2-core ARM9 processor on it, as well as a field programmable gate array built in. Oops. Here is a computer which I feel is reasonable for university students. A 2-core ARM9 processor, a field programmable gate array built in, and some digital signal processing chips to teach you how to program those. But it also has a 16-core CPU where each core of the CPU has 32 kilobytes of memory that it can store its own program in and its own data and have true parallel programming at the same time. This costs, in its smaller form, $99 US. The larger and more powerful one is $249, but that's within affordability for a university program. And it only uses 5 watts of power. This is the explanation of it in detail. It's quite a powerful system, but this is what I think university students should be learning to program. So when you talk about performance, you have to look at the different categories of performance. First of all, there's the speed up of your program. Does it take 10 hours to run or 3 minutes? The memory utilization. Are you going to be putting your program into an embedded system or into a phone, and you're limited with how much memory you have? What are the trade-offs that you're going to be making? Cache utilization. If the CPU you have has a lot of cache in it, you want to be able to try and keep your data as close together so that you have something known as reference of locality or reference of time, temporal locality, to try and use your cache as much as possible. Think about using different algorithm replacements. There's a book called The Art of Computer Programming, written by a man named Donald Knuth. And volume 3 of that book is Searching and Sorting Techniques. Dr. Knuth has had to rewrite the book 3 times in his lifetime because his memories went from 16-bit to 32 and 32 to 64. He had to change algorithms. Sometimes you do the same thing over and over again. Try and think about creating an intrinsic for the compiler to do that so that you can work on making that intrinsic very, very efficient, and you free up programmers from having to worry about how to do that particular thing. There's other compiler and performance improvements. If you're really interested in this work, then you might think about joining one of the compiler projects. It's fascinating. And all these things, we didn't even know we would have them 20 or 30 years ago. Now they're becoming commonplace. So if you want to go and study this type of work, first of all, you can learn a really cool assembly language, and they are really cool. But please, don't code in them. But you can learn code analysis techniques, how your code works and how it uses the memory of the computer. And this will allow you to create better code overall, even if you're using Java. Really, your Java code will probably improve 10 or 15% just by storing your data the proper way. You will create an open source portfolio that you can take to potential employers, and you can say, this is the work I've done, and trust me, they will recognize what you've done, and you will get a much better job than somebody who just writes in Java. If you're a university professor, you might consider creating a course in optimization for your students to show them how much faster they can make their programs run. And if you're a researcher, let's look at the new optimization techniques, such as automatic detection of race conditions. For those of you who would like to look and start down this path, here are some resources that you could look at. And a few more resources in ARM assembly language. And now I will put in one last advertisement for something which is happening here in Argentina. There is a project to create a completely open industrial computer, which is being designed and built here in Argentina. It's a nice project, and if you'd like to work on this type of thing, I suggest that you join the project and work on it. And that, I thank you very much. Do we have any time for questions?
Yes.
Okay.
Ahí está, ahí funciona. Thank you so much, John. Muchas gracias en nombre de Campus Party también por la disertación que ya él viene dando hace varios Campus Party, así que es ya un miembro de la casa. Para los que no saben, este dispositivo que tengo acá, Catchbox, es para hacer una pregunta. Así que, ¿alguno tiene ganas de hacer una pregunta, John? ¿Nadie? ¿Alguno? ¿Nadie? ¿Quién se anima? Dale, el primero. ¿Quién se anima? ¿Se anima? Bueno, vamos a tirarlo a ver si llega. ¿Tiene micrófono también? ¿Se lo alcanzan? Porfa.
I will also tell you that I will be around all of Campus Party, and I'll probably be hanging out there in the Sys Army tables, so if you want to ask a question, please. I'd actually rather have you ask a question and talk to you than just have you take a picture and run away.
Here we have a question. Sí, hablale por favor al Catchbox.
Hello. Well, I would like to know what do you think about the future of Linux for homes, I don't know, for the desktop.
The future of Linux. It's interesting because back in the 1970s, when I was working with Unix, we would say to ourselves, I don't know what the next operating system is going to be, but I bet it will be compatible with Unix. And I said, I don't know what the next operating system will be, but I bet it will end in the letter X. And I was right. I don't know, I mean, with quantum computing, we might see a completely different type of kernel or something like that. But I'll tell you one thing, I think the entire industry is tired of trying to keep porting programs over and over to different operating systems. And I think that there will be some type of Linux compatibility that will be built in, which will allow that to go faster. But I really don't care if it's Linux or not. What I do care about is that it's open and that end user customers have the freedom to be able to make their operating system and their software do what they want to. That's the most important thing.
Thanks, John. ¿Alguna otra pregunta? John, do you want to throw the Catchbox or I will throw it?
I'd be lucky to have to see them.
Here we have one.
Okay.
So, vamos.
Hey!
Perfect. Bingo.
Nice. Yo soy docente y vemos que todo lo que estamos hablando ahora es de muy bajo nivel. ¿Alguien le traduce?
Sí, yo le traduzco. He's a teacher and all the topics he is seeing are low level basically.
Y encontramos en la programación, cuando enseñamos a chicos, problemas pedagógicos porque la programación es muy abstracta.
And we found, when we are learning to code, we found a lot of problems because coding is abstract, generally.
El acercamiento al hardware es mucho más concreto. ¿Hay algunas herramientas o recursos para enseñar este tipo de cuestiones de bajo nivel en hardware? Si él conoce para, digamos, que estén como pedagógicamente más sencillas de entender, que no sean tan abstractas.
He comparing coding to hardware, software to hardware, and to getting closer to hardware. We have a lot of more tools that we can see and we can touch. If you, he's asking basically if you know any tool that can help coding to be more visual and have a more close look to hardware.
I think those two things are actually kind of separate from each other. Unfortunately, programming is still, as you say, a creative art. It is, I mean, it's very, I belong to the Linux Professional Institute, and we do certification of systems administrators. That's relatively easy to do. But certification of programmers is a lot harder because there's so many ways to write a program to do the same thing. What is the correct way? And a program, let's use a simple example, a program to sort numbers makes a difference whether you have a server system with 16 gigabytes of memory and it's a virtual memory system versus an embedded system where you only have half a gigabyte of memory and you have to fit everything into that. So you would attack that problem, the same sorting problem, a different way. And you just have to kind of teach that through experience, or at least get the students to understand what the criteria are. Why are you doing that? So, but when you say that a lot of things I talked about are low level, getting the student to understand that the machine will hold a number a particular way, and to force that language to store the number the way the machine holds it in its most natural state, that's something that everybody should know, no matter what language they write in. And or trying to keep all of your data together and being accessed, cell by cell, so that it stays inside of cache, is another thing they should be taught. One of the things I skipped over in my talk was a friend of mine had two very large arrays that they were going to multiply together. And they wrote the program just like a high school student in algebra would write the program to multiply the array. And the first array was fine, going across the rows. He kept getting the numbers staying in cache, everything was fine. But with the second array, every time it was so large, every time he went after the next number, he had a cache miss. And that time it took to do that cache miss made his program run 40 times slower. So he took the second array and he inverted it. And now, every time he accessed the number, it tended to stay in cache. And when he did the multiplication and inverted the answer, which gave him the same results, it went 40 times faster. These are the types of things that you say. And once the student has learned it, it becomes second nature. Your mind creates this hardware interrupt when you're doing something. You go, I need to store it like that. Okay. But you need to get them, they have to know the information first, or else they don't know what to do. I spent the first 7 years of my life out of university. My job was to take other people's programs and make them run faster. And my boss told me, if you can't make their program run at least twice as fast, don't waste your time. It was kind of sad that I could take a person who was supposedly a good programmer and make their program run 5, 10, or 15 times faster. Or in the case of one person, 220 times faster. Next question. Oh,
Thanks.
Way over there.
Thanks, John. We will make the last question. Vamos a hacer la última pregunta. Ayúdenme con el catchboard. Ahí por... Uy.
I would have thrown it to the person closer to myself. I mean,
Y por ahí.
I had a heart attack last May. I could probably only get the ball out,
Perfecto.
Hey, John, a pleasure to meet you here. I come from the hardware industry and I'm a technology fan, but I'm not a programmer. But I'm aware of many things about the topics. So I have two questions for you. Would like to hear what's your opinion about JSON, Java System Objects Notation. I've heard that you hate Java. So what do you think about JSON? And you also talked a lot about hardware. That's what I really understand, but I see so many trends moving to the cloud. So those are my two questions for you. Opinions about JSON and cloud. Thanks a lot.
Well, unfortunately, I haven't looked at JSON enough to really have an opinion on it, so I'd like to skip over that question. The second one is, I've been in the computer industry for 47 years. I think I've seen everything from clouds to fog, and I think we're into the fog mode right now. I mean, we say the cloud as if there's not machines at the bottom of it, and there are. I mean, everything is a machine, and like I said, Google, if you program right, Google might be able to only buy 9,000 servers instead of 10,000 servers. There's a certain amount of workload that they have, and writing a program efficiently saves real money. I give another talk about what I call the software gap. the gap between what the software really does and what the people really want the software to do. And a lot of times that gap is really small, and you only waste maybe 5 minutes a day with that little gap. Or you say, oh, you waste 15 pesos a day because of that little gap. But there's 2 billion computers on the face of the planet, and so 15 pesos times 2 billion means it's 30 billion pesos that we waste every day because the software doesn't work the way we want it to. That's enough to inoculate every child on the surface of the earth against polio and wipe out the disease forever. It's enough to actually cure world hunger. And we don't see it because we only waste 15 pesos per person per day. If you say you waste 15 minutes a day and you have a call center with 300 people, that's just as if 9 people never showed up to work. And if you were a manager, you'd be furious that 9 people didn't show up to work. They didn't call in sick. They're not on vacation. They're not being trained. They just didn't show up. But now, let's take one of those people and train them to be a really good systems administrator. Somebody that will tune your operating system to work the way it should. Somebody that will make sure that all of your backups are done. Somebody get rid of your spam and get rid of your viruses and things like that. And magically, 6 people will show up again because they'll save that 15 minutes a day. And that's why I object to the concept that most IT managers have that a systems administrator is an expense. They are not. They're an asset to your company, and you should use them that way. And you should pay them that way. Did I answer your question? You're welcome.
Gracias. Thanks.
Thank you very much for coming.
Un aplauso enorme para John Maddog Cole otra vez.